Hello everyone, how are you today? Today we are gonna be talking about a problem called maximum profits. Its difficulty is between bronze and silver, and it's a very classic problem. Specifically, it is a part of a bigger problem called maximum independent set, which is a concept in graph theory. Now, I recommend you to think about this problem for a while, and now I will eat the watermelon. So, I bet you have already have some ideas. And now I will start from a more general problem of maximum independent set in the graph. So, an independent set is a set of vertices such that no two vertices in that set are adjacent. And a maximum independent set is an independent set such that the sum of values of these vertices in that set is maximized. So in an arbitrary graph, the maximum independent set can be solved by O n squared times 2 to the nth power time complexity. And it is NP hard, meaning that currently there is no polynomial time complexity to solve that problem. So what about a tree? In a tree, the maximum independent set can be solved way more faster because the property of a tree can be used to derive a dynamic programming solution. So we can consider every subtree, right? So suppose we already know the maximum independent set of a subtree, then how do we use those information to get the maximum independent set of the whole tree? Suppose that now we want to get an maximum independent set of a subtree. And there are two possibilities. One is that the root is occupied, meaning the root is chosen in the maximum independent set. From now on, I will use MIS to refer to the maximum independent set to be faster. So one possibility is that the root is chosen, meaning the root is part of the MIS. In that case, none of its children can be chosen as a part of MIS. So the MIS of the subtree in this case is the MIS of all its children, and with a condition that none of these MIS can contain the root itself. So at this point, we realize that an information is very important, which is whether the root is occupied or not. So we can use that as our DP state. More specifically, DPU0 denote the MIS of subtree U when U is not chosen as a part of MIS, and DPU1 denote the MIS of subtree U when U is chosen as a part of MIS. So, as we have covered before, DPU1 can be get from the sum of DPV0, where V is a children of U. We are the children of U. So the MIS of subtree U is the sum of the MIS of all its children, given the condition that none of this MIS contains the root, plus 1, where 1 is the U itself. And how do we get DPU1? DPU0. Similarly, DPU0, in DPU0, the U node is not chosen. So we can choose the children of U freely, meaning that we can decide whether to choose the children of U or not. So DPU0 is the sum of DPV1, where V is a child of U. To summarize and explain again, the maximum independent set of a tree is can have two possibilities. One is that the root is chosen, and another is that the root is not chosen. When the root is chosen, we can't choose the children of the root anymore. So we want to first calculate the maximum independent set of all the children, all the subtree of U, all the subtree of the original tree, where the children is the root. And because we can't choose those children, DPU1 can only be calculated through the sum of DPV0. And when the root itself is not chosen, we can whether choose the children of U or not choose the children of U. So DPU0 can be calculated through the sum of DPV1, the maximum value of DPV1 and DPV0. So this is a fantastic application of dynamic programming. When not using dynamic programming, we can only calculate the maximum independent set in a not even polynomial. Is exponential time complexity. However, when adopting the dynamic programming, we can optimize the time complexity to O of n. And if you have any questions, feel free to contact me. And I can also invite you to have a working man.